ways very different because polar graphs just act and behave a lot differently than rectangular. So when it comes to polar area, I think the easiest thing to kind of connect it to is the area of a sector, because that's kind of how we're going to treat polar area. Like a circle in many ways is like the most simple version of a polar graph. It's a graph you can trace out around an origin with like a clear like r is equal to 5, r is equal to 6. It's the easiest polar graph you can make. And in many ways, all other polar graphs are just like a circle with the r changing, hence r being a function. So not really a circle, but same idea. So we know in general the area of a circle, I hope, but area of a circle we know is just pi r squared. Duh. We also can kind of easily figure out the area of a sector. And a sector is basically a part of a circle, is a fraction of a circle. So we know that a circle is pi r squared, and we want a fraction of the circle. Well, that fraction will be described as some angle. What is going to be the angle of a full circle? 360 we're in degrees, but this is calculus, we're always in radians, so it would be 2 pi. So theta over 2 pi is kind of like the long version of the area of a sector. Simplifying this is the same thing as saying 1/2 the pi's cancel, r squared times theta is how we often write it. So this is the formula of a sector. That is the area of basically like a pizza slice, if you will, with theta, of course, being measured in radians. If you're doing the formula in degrees, it would be like theta over 360 pi r squared would be a different formula. But this one is in radians because that is how we do calculus. Why am I showing you this? Because basically we're going to use the idea of the area of a sector to find the area of a polar graph. Why is that? Reminding ourselves how we find area in the Cartesian plane, we're going to kind of connect the rectangular area in Cartesian coordinates to the area in a polar graph. So when we think about the area in its rectangular form, it's simply the integral from a to b of your function with respect to dx. Where ultimately did that come from? Remember why that formula works. F of x is representing basically the y coordinate. So it's like you have the y coordinate and then you have the dx. And what that's basically representing is you have the height and then you have the base. What the integral does is it basically adds up all those rectangles, and that's why we have the area. We're basically doing the f of x is like the base, and the d of x, actually let me reverse it. The f of x is like the height, and the d of x is like the base. It's basically referring to the area of a rectangle. When we talk about polar coordinates, it's going to be similar, but in polar coordinates, we never kind of measure from the x-axis. Like when we graph in the rectangular form, it's like x comma y. In polar graphs, it's always r comma theta. So we're never measuring from the x-axis. We're always measuring from the pole. So if this is a polar graph now, how I would find its area is I kind of imagine all these itty-bitty skinny sectors. Clearly, I'm not going to draw all of them. But we have all these itty-bitty sectors kind of like fanning out from the center. And then when you add up the area of all those sectors, that's going to give you the area of the graph. The area in polar form, so here's going to be your new formula. It's going to be the integral. We often write it from alpha to beta just because those are representing angles and not x values, but if you wrote a to b, clearly the same thing. From some starting point to some ending point. What's the area of a sector? 1/2 r squared times theta. We're going to write it as 1/2 r squared d theta. This is the area of a curve in polar form. So we have the integral from a to b, and it's always 1/2 r squared d theta. So it's not going to be like a top minus the bottom. It's not going to be, right to left, left to right, top to bottom. It's just going to be 1/2 r squared d theta. Now there are some things that we have to be careful with, and why I think finding the area of polar graphs is more tedious than difficult is there are some things you have to be careful with. So for example, I kind of typed in this first part here because it does seem kind of wordy. For that formula to work, I'm just going to kind of rewrite it out here. We know the integral is going to be from alpha to beta, 1/2 of r squared d theta. For this formula to work, I have r of theta must either be non-negative or non-positive on all of a to b for it to work. What does that basically mean? That means that when you have that interval, the starting point to the ending point, that r value cannot change signs. So it has to be always positive or always negative. And so that's me kind of translating that in other terms. R cannot change signs with an interval. And so then we want to think, if it can't change signs in the interval, we want to be careful, like, hey, well, where is it possibly going to change signs? R possibly changes signs when graph crosses the pole. And then adding on to that some more, when is the graph often going to cross the pole? That's going to occur when your r value is equal to 0. So we are going to have a lot of things that we need to consider. So basically what I'm saying, if I can have an example of this, if I say I'm integrating this from 0 to pi over 2, that means that between 0 and pi over 2, this graph can't go back to the origin, because there's a big likelihood that's going to change from a positive r to a negative r. Another thing that I think is going to be kind of tricky for a lot of you, and why a lot of you will kind of hate this topic, just to kind of put it out here, is that there's typically going to be an infinite number of integrals that you can write that would all be the exact same and correct answer. So I want you to think about why that may be. This is a polar graph, so everything's based on the circle. We know that coterminal angles are the same. Like you might say, hey, I want to integrate this from 0 to pi over 6. Your neighbor says, hey, I'm integrating this from 2 pi to 13 pi over 6. Guess what? Y'all are both going to be correct because that's still talking about the same region when looking at the graph. Also, it makes it kind of a big pain to grade, but that's going to be something that's true when we're looking at these graphs. The other thing I would add to here is we are going to rely on symmetry a lot. And what I mean by that, if we're looking at a graph, instead of maybe writing an integral for the entire region, I might say like, oh, this region I can easily divide in half. Let me just write an integral for the first half and then multiply my answer by 2. And that way we're going to avoid some of the strange mistakes we can happen when r is crossing the pole. So these problems, again, I call them more tedious than difficult. And I will say when I have 4 examples, I try to choose 4 different types of problems. The answer I end up putting on the board is definitely not the only answer. There's always going to be more than one way to write the integral. So if you like look at it and think of a different way to write it, like we can just like talk about it and see if that answer would work as well. One thing that I find about these problems is they really are tedious. And they're the type of problem where I'm just going to say like, let's not rush it. Like, let's just make sure we take it slow and make sure we find like the nice starting point and then also the nice ending point. Here's the most basic example, what I think is also the easiest example to look at. So I have set up, but do not evaluate an integral for the area of that yellow region. It's in quadrant 2, bounded by the coordinate axis, the x-axis, the x and y axis, and then we have the graph. R is equal to 4 times 1 minus the cosine of theta. So if I'm doing this one, I think this one's going to be pretty easy to do. First off, we only have one graph. So I'm going to go ahead and write down the integral that I'm using. So I know that I'm going to have the integral. We have 1/2 of r squared d theta. And what is r? R is 4 times 1 minus the cosine of theta. What I need to find now is I need to find the starting angle and the ending angle. And we're going to use the graph to help us figure this out. Now, I will say when it comes to the graph, most of the time on the AP exam, they will give you the graph. If not, you would have a calculator, you would be able to graph it. You wouldn't be expected to know what this graph looks like without a calculator or without it provided in front of you. And when I say why this is tedious, you always just want to double check what you think the answer should be. So we are integrating this where we want to find the starting angle and we want to find the ending angle. I sometimes think in terms of like, okay, most of the time the angle's moving in like a counterclockwise direction, but we don't always know which way this graph is being traced out. You could easily put it in the calculator and kind of see which way it's going. But I first say, okay, if I'm looking at this region in yellow, here's a starting point and here's an ending point. Remember when we were looking at these problems, there's not really a top to bottom, it's more like the graph to the origin. So that's kind of how we're looking at it. So we're kind of thinking like, there's a sector, there's a sector, there's a sector, there's an infinite of them, but that's kind of the idea that we're thinking about it. All those little lines are going to connect to form the full area. So we basically need to figure out, well, what angle is going to start this region and what area is going to end this region. Here's where it gets tedious. We're just going to pick an answer and guess and make sure it works. What angle does it appear this region is starting at? Pi over 2, right? So that's going to be up. It is pi over 2. And when I say you're like, well, duh, that's pi over 2. Let's talk about what that means. Your theta could be pi over 2. But if I'm up there at the top, technically what other angle could I say that is? It could be 3 pi over 2. If we're saying it's 3 pi over 2, what's basically your R value going to be? A negative value, right? Negative 4. And so when I say it's pi over 2, like that's not the only option. Like 1 pi over 2 is the same thing as 5 pi over 2. Is the same thing as 9 pi over 2. Like all those are the same. We can technically choose any starting point we want. For me, I like choosing a positive R as much as possible. I like dealing with positive numbers. Positive R's are going to be nice. I also like to choose angles close to 0 radians. So like I don't like getting too far away from 0 just because I don't want to make sure I skip over a chance where it's crossing the pole and messing things up. Let's check to make sure pi over 2 works. So again, I don't want to use 3 pi over 2. Let's just check it. And when I say check it, let's plug it in. So I have 4 times 1 minus the cosine of pi over 2. The cosine of pi over 2 is 0. So I have 4 times 1. My R value is positive here. That is greater than 0. Again, when I have to write that down, know that might be something I just kind of check in my head. But again, for this formula to work, your R has to remain always non-negative or always non-positive. So I'm looking for, I need a positive R, I just want to make sure it stays positive. That works, pi over 2 works. So I'm going to go ahead and start it at pi over 2. And now I just want to pick and guess an angle of where this area is ending at. What angle do you think is going to be your guess first of where this area could end at? Pi. And again, you do want to check it. And again, I want to check it because if this gives me a negative number, then I need to find something smaller than it to make sure it works. So I have the cosine of pi. Cosine of pi is negative 1. 1 minus negative 1 gives you 2. 8. It's positive. We're good to go. This answer is how I leave it. I've set it up. Some things about your answer. Polar area will always be positive. The angles will always go in order. So you're always going to go from the smaller one to the larger one. And as a general rule, I'm not going to really write this down, but as a general rule, you want those two angles to be as close as possible. Like for example, pi is the same thing as 3 pi. You wouldn't want to say this is going from pi over 2 to 3 pi. You want to do the two angles that will be closest to each other. Again, that's not the only answer. You could have said the same problem using like coterminal angles. Well, so you could have set it up as like pi over 2 plus 2 pi and like pi plus 2 pi. Those are coterminal angles. It would give you the same area. It would represent the same shape. Again, it tends to be easier though if you're going to choose the smallest version of those, just to kind of be a little bit consistent. And that's the basic example. So any questions on that before we do some of the more complex ones? All right, so let's go ahead and try another one. The second type of example,
Mr. Brown.
in here. So if I'm looking at this one, we're going to set up and not evaluate an integral expression for the area of the common interior of r of theta, which I have in red, and s of theta, which I have in blue. So what are we ultimately trying to find? We want to find the area of this region. So let's talk about this region, because again, polar graphs are weird. They behave differently than the other graphs that we have. There's no like top minus the bottom always. There's not going to be like a right minus the left, because everything is being measured from the origin. So first way, and again, this is not the only way to do it, I like using symmetry, because sometimes when you start having integrals where the angles are too far apart, weird things can happen along that interval. So it's going to be nice to just use a smaller region. What I mean by that is if I just found the area of this top half, what can I do with the area of that top half to just have the total area? Double it, multiply it by 2. And I'm going to make the argument that doing the top half is going to be easier than the whole piece. You're less likely to run into mistakes. And then what's also weird about this one is it is technically still going to require 2 integrals. It's probably not how you expect it. So watch how I kind of draw this. Polar graphs, when you find the area, you always go from the origin out to the edge of the graph through the region. So when I think about those sectors, always measuring from the pole, and I'm actually going to use little segments, make sure I draw straight lines. So here's like one representative segment. Notice which graph you're touching. Like there's another one I can form here. I guess we're going to keep selecting a straight line. Like there's another segment. But notice as you keep kind of going around, now this graph is on the outside as you kind of get closer and closer to the origin. So we are going to have 2 integrals. Where are we going to split those 2 integrals at? We're splitting those 2 integrals at basically at that intersection point, which now that looks ugly. I'll just draw it by hand. Where am I splitting it at? I'm splitting it right there. So again, there's not going to be like a top to bottom, right to left. You want to think about going from the origin out, which graph you're touching. So when I'm looking at this one, we do have like that red one to deal with, and then we also have that blue one to deal with. We also have that dividing point where we switch between the 2. So lots of things going on. We're still going to want to test our points and making sure that R stays always positive or R stays always negative. Let's talk about the easy part first, I think. Those 2 graphs have an intersection point. That's where the area is switching from being bounded by the red one and being bounded by the blue one. How can I go ahead and find that intersection point? Set them equal to each other. So we can do that. That's something that's easy to do. So I have -3 cosine of theta is equal to 1 minus cosine of theta. So -2 cosine of theta is equal to 1. Cosine of theta is equal to -1/2. When does that happen? Several times. 2 pi over 3, 5 pi over 3. And we know that basically continues forever. We can keep finding values. If I want to choose like the smart one, what's going to be the best one that I probably want to start with first? 2 pi over 3. We want to choose ones that are like smaller and closer to 0. So those typically are going to be the easier ones to deal with. So I know I'm going to have an integral. And we need to start kind of thinking about where that ends at. So now let's think about if we can find a place where this area starts at. And again, we're talking about the red one. How can I figure out where this area might start at, or what angle would you guess this area might start at? And this is where you have to kind of think through it. So maybe 0. So let's try something. So here's the starting point, right? Like I see this area traces around. Let's try when theta is equal to 0. This is when it's touching the red graph. At theta is equal to 0, I have -3 cosine of 0. What's the cosine of 0? 1. So this is -3. So it's less than 0, which is not necessarily a bad thing. No, like you can use -r as long as you make sure it's negative within that entire interval. Well, we already said that this area is ending at 2 pi over 3. So this is where it kind of gets tedious and where we have to kind of check stuff. This area was ending at 2 pi over 3. That's that point on the graph. Let's see if at that 2 pi over 3 we have a positive area or a negative area. So that's going to affect what we start with. So when theta is 2 pi over 3, let's plug it in. This is going to be an r. R is equal to -3 cosine of 2 pi over 3. Well, what's the cosine of 2 pi over 3? Positive or negative? Negative, which is going to make this greater than 0. Can we use a -r and a positive r in the same integral? No, I mean, something's happening there. It's either crossing the axis, something's happening there, so we need to find something different. And this is where you kind of want to think, well, like, yes, this is just the origin, so we picked 0, but what might have been another angle we could have picked instead? 2 pi, let's choose something smaller. We already saw that. Pi, let's try another one. And again, I'm being smart about this. 2 pi over 3 is my top one. Let's try pi over 2. So again, we want to make sure we're staying within those bounds. Let's try theta is equal to pi over 2. Well, when theta is equal to pi over 2, we have -3 cosine of pi over 2. What's the cosine of pi over 2? 0. Which is that answer going to be okay? Yes, because we know that this is starting at the pole. 0 would mean we are at the pole. That's where that area is starting at. So this first integral is going to go from pi over 2 to 2 pi over 3. Again, those angles are in order. They're close together. And then that was the one from 1/2, the red one, 1/2 r squared d theta. We did all that work in the area of basically this tiny little sliver. Now we need to finish this one out. Well, this integral is going to pick up at 2 pi over 3. We need to figure out where it's going to end at, and now we are on the blue graph. What might be a good guess for an angle of where this one is ending at? And here's where it's ending at if I'm looking at it visually. Pi, so let's try it. So I have 1 minus the cosine of pi. What's the cosine of pi? -1, 1 minus -1, that's going to be a positive value. Is that what I wanted? Yeah, 2 pi over 3 was a positive r. I want to keep a positive r. And then I have 1/2 r squared d theta. Make sure you go back and answer the question. This was asking for the area between those two graphs. This would just be the top half. So I want to take this entire integral and multiply it by 2. So you can see, and again, I want to say things clearly, that's not the only possible answer. You could have written an integral that covered the whole region without having to multiply by 2. You could have used like coterminal angles, you could have used negative angles, but the basic idea is, and in general, you want the angles you use to be close together. The r value can't change signs between those intervals. It can be 0, but it can't go from like positive to negative. And a lot of this, I'm going to be honest, is just like you practicing and kind of getting a feel for how those angles are going to work. Seth, you had a question, and I'll see if I can answer.
So why are you using r of theta for the first interval and s of theta for the second one?
Because, good question, when I'm looking at it, I'm just going to erase all of this that I have. You're always measuring from the pole, and you're going through the region to the edge. So this first part, if you're going from the pole to the region, you're touching the red one. That's giving you your r. How far are you away from the origin? Your r away, coming from the red one. But how far away from the origin on this side of the area, that's going to be your function s.
Okay.
Where did that change happen at? That happened at 2 pi over 3. So normally we're used to going from like the axis down to, or the graph down to the x-axis. Now we're always going to go from the graph into the polar origin.
Okay.
Anyone at home have any questions about that problem?
If it goes
Alright,
from
Go ahead, sorry. 1 second, let me turn the sound up. All right, go ahead.
I was gonna say, why can we use pi over 2? I didn't understand how you got that angle. Like why can't we use then like pi over 3 or pi over 6? Like why did we use pi over 2?
Why did I use pi over 2? I guess another way I could have said this one, so typically we're able to pick kind of key values, and I guess you have to remember from pre-calc how these graphs look. So like you could easily make a t-chart and kind of start finding these values. My thinking is like these graphs are still based off of circles, so like important things are often going to happen at those key angles. Another way of how you could have gotten this pi over 2 is you honestly could have just set it equal to 0 and go from there. But I just know from experience it's going to be easier to pick ones that you know are going to work and kind of go from there. Let's try this third one and see how we do.
Mr. Brown,
Yes, Den.
is it okay if it goes from negative to 0 then?
Yes, so as long as it's non-negative the whole time or non-positive the whole time.
All right.
So as long as it's not switching from negative to positive, you're good. Let's talk about this one. This one does say find the area, so we are going to actually evaluate in the calculator. That's just going to be one extra step. And we want to find the area enclosed by this 3-petal rose. Now, the biggest mistake I see on this one is people are just like, oh, it's the full graph, let's just integrate it from 0 to 2 pi. And I can tell you if you integrate from 2 pi, you're going to have actually more area than you need because it's going to overlap on itself. So you do have to kind of be a little bit smart in how you do it. Other ways you can be smart, instead of finding the area of all 3 petals, what could you do instead? Find 1 petal and multiply it by 3. Does it matter which petal you find? No. For me, though, the easiest petal to find is going to be the first one you hit. But ultimately, you can find any petal and then just multiply it by 3. How are we going to be able to find where this petal is going to start and end at? When r is equal to 0. So that petal is kind of switching at the polar origin. So that's going to happen when r is equal to 0. So we do have when sine of 3 theta is equal to 0. So when the sine of something is equal to 0. Well, when is the sine of something going to be equal to 0? Sine is equal to 0 at 0 and pi. But we're going to set 3 theta equal to that. So I get theta is equal to 0. Theta is equal to pi over 3. I will say we can technically stop here, which is nice. But if we want to keep finding polar intersections, what we need to do to each of those answers? Add 2 pi over b. So like the period of this graph is 2 pi over 3. So like it crosses at 0, but it also crosses at 2 pi over 3, 4 pi over 3, and that's just going to continue forever. Same thing with pi over 3. That's going to cross at 3 pi over 3, which I know is pi, 5 pi over 3, and that's going to continue forever. What that basically means, so like if I were to trace this out, at 0 is at the origin, so we have 0, then we have pi over 3, then we have 2 pi over 3, then we have pi, 4 pi over 3, yeah, I said it, 2 pi, well no, 2 pi over 3 is at 0, so yes, it keeps going around. But basically it's going to go around, and every time you get to one of those angles, it's hit the origin. What we need to figure out though, and what we're not going to overcomplicate about it, is if we're just trying to find the area of 1 petal, based off of the algebra that we did, where is 1 petal going to start at? 0, and then what's the next value that comes after it? Pi over 3. And then we have the area formula, 1/2 r squared d theta. That's one petal. We need to find 3 petals, so multiply it by 3. To be clear though, for a curve like this, any 2 angles that are next to each other would give you the same answer. So for example, you may say, hey, I'm starting one petal at pi over 3. What's the radian measure that comes immediately after pi over 3? Like you could have used 2 pi over 3 and still multiply that by 3 and get the same answer. In your calculator, I will say it doesn't matter if you are in functional mode, parametric mode, or polar mode. They all will give you the same answer. So whether you're typing in x in your calculator or theta or t, they will give you all the same answer. Just make sure you're of course in radians and not in degrees. So for mine, I have 3 times math 9, and this is from 0 to pi over 3. And I have 1/2 of r squared, 6 sine of 3. Mine's in function mode, so I typed in 3x. Don't forget the squared, and dx. Of course, the calculator doesn't know what it should be in. And the area we should get, I get 28.27. Questions on that? Just to show you that there's an infinite way to rewrite it. As long as you have one petal and multiply by 3, you're going to get the same answer.
You're setting r equals 0 to find where it intersects the pole, right?
Yes.
Okay.
Is there a kind of question where they'll give you the formula and then the interval will just be like, what's the area over this interval and just plug it in? Or is that too?
Nah, they wouldn't give you that. They will always give you the graph. They'll always give you the function. And then you kind of solve it from there. The tricky part, again, with polar areas is often like, I think for me at least, finding the starting and ending angles. But in general, you just want them, it's easy when it's close to 0 and they're close to each other because you don't want it to pass through anything weird. What time is it? Let's try to squeeze in one more. I think this is going to be the most challenging one to kind of think about. So let's look at this one and then we'll see kind of where we're at. So I have this yellow region. It lies between the inner and outer loops. This is Riemann-Son. Don't need to know that, but the graph is provided. R is equal to 1 minus 2 sine of theta. And we want to write, but not evaluate an integral expression for that area. So when I'm looking at this problem, let's just go ahead and get out of the way. Like there are going to have to be some subtraction here. So when I think about like the R value, we're always measuring like from the pole. So we have like, there's 1 R, but then we also have some empty space that we're going to have to subtract out. So it is going to require 2 integrals. There are 2 ways we can do this problem. My preference is typically just to do the area of half of it and then multiply it by 2. You can also do the area of the entire thing. It would work the same way. And basically we need to remind ourselves kind of how the Riemann-Sons kind of work and things like that. In general, key points in the Riemann-Sons, the ones that you're going to see, are going to happen at the 0, pi over 2, pi, 3 pi over 2, and all those coterminal angles. When we're writing our 2 integrals, the way I'm going to think about it is we'll basically have the outer loop one, and then we're going to have to subtract from that the inner loop. And we just need to find like a good starting point and a good ending point. One trick I will show you, if you do have a calculator, so I'm actually going to switch the screen over. I didn't do this in 3rd period, and I wish I had, because I think it does clear up some things, and I'll probably do it for them tomorrow, or definitely do it for them tomorrow. In your calculator, you can actually graph this in rectangular mode to give you an idea of what the inner and outer loop is kind of looking like and starting with. So again, I'm going to put this in function mode. Again, we can't just treat it like a function mode problem, but it can give you an idea of what it looks like. So in function mode, I'm going to type in its relative, which would be 1 minus 2 sine of t, or sine of x since I am in function mode. And I'm going to hit zoom trig, actually, zoom 7. And it gives me that graph. How this graph relates to the limacon that you're looking at. This part above the axis, that is you tracing the outer loop. That's the bigger one. The time where you go below the axis, that's representing the inside loop. So you can see some similarities, like this outer loop goes out to 3. The maximum peak is 3. The inside loop goes to -1, like you are like 1 below the x-axis. Basically, each time this crosses the x-axis is the same thing as this graph crossing the pole. We kind of have like taken a graph that was linear, and now it's just being spun around the pole instead. So when I'm thinking about this problem and different ways to approach it, I need to figure out, if I'm doing the whole graph, like where it is from start to end on the outer loop, minus where it's at start to end for the inside loop. Different ways you can do that, but I think the easiest way when you're kind of looking at this, what is the R value going to be when this is crossing the pole, where it's basically switching between the inner and the outer loops? 0. So like, how am I going to start off this problem? Let's just go ahead and set it equal to 0 and kind of go from there and play around with it from there. So go ahead and solve that equation for me. And again, why we're doing this, this is going to tell us where it crosses the pole, which is potentially going to be the place where the R value is going to switch from negative to positive, where also the inside loop and the outer loop are going to kind of switch places. So solving this, you're going to get sine of theta became positive divided by 2. Sine of theta is equal to 1/2. So then theta, when is sine equal to 1/2? Pi over 6, 5 pi over 6, and like all the coterminal angles of those. So like pi over 6 can also be, 13 pi over 6, 5 pi over 6. We can also write, but all the coterminal angles of those also works. The other way that I'm going to think about this one, again, you don't have to do it this way, but I'm just going to write an area for half of it. You might argue that doing the full area is just as easy. I'm going to do half of it and then just multiply it by 2. The reason why I do that is, for me, it's going to be easiest to keep things close together in doing my problem. So since I am doing half of it, I know that like whatever integrals I end up writing, I'm going to go ahead and multiply it by 2. And again, you could play around with it and just do it as from the entire loop. Let's do this outside loop first. When I'm looking at this outside loop, I see that this is tracing from, if I'm just doing half of it, from here, and then we're tracing around. Where's it going to stop at? It's going to stop at that angle. We do know kind of what one of those angles that's stopping at is. What's going to be at least one of the angles we want to use for where that outside loop is stopping at? Pi over 6. Is that maybe the only possibility? Maybe not, but I see this is a tangent line. This is when theta is equal to pi over 6. So I know that that's going to be one of the angles that I stop at. So now I do want to think about where this stops at or starts at, if I'm thinking about it in terms of just half the region. 2 ways to think about it. If you want to solve an equation, this is when r is equal to 3. But these graphs do follow logically what might be an angle you attempt to try first to see if it's going to work. 3 pi over 2. That's on the bottom of kind of like a unit circle. Let's try 3 pi over 2. When I plug 3 pi over 2 in, I have 1 minus 2 sine of 3 pi over 2. Well, the sine of 3 pi over 2 is -1, so we have 1 minus 2 times -1, which is going to give you 3, which makes sense. That's crossing where it's 3. Again, the other way to do that is write an equation, set it equal to 3 and solve, but most are going to be easier, kind of guess and check. So now we have a dilemma that we want to think about. This is 3 pi over 2 to pi over 6. In general, we want our angles to be as close as possible. I know that if I'm looking at 3 pi over 2 to pi over 6, in that order, it crosses over 5 pi over 6. And weird things can happen when you cross the origin, like r can change signs from negative to positive. So if I'm trying to find angles that are close together but equivalent, what might be something I want to use instead of 3 pi over 2? Negative pi over 2. So you want things to be close to 0, close to each other so you're not crossing over things awkwardly. So I would argue that negative pi over 2 to pi over 6 is the best answer for that interval. Now, is that the only one you could have used? Definitely not. You could have done the integral, like if you really wanted to use 3 pi over 2. Instead of using pi over 6, what angle would you have to use as your stopping point? So it would still be the same angle at pi over 6, but it would need to be something after 3 pi over 2, so it would have to be 13 pi over 6. So again, like you can argue maybe that one, like I had some people in third period, and they're like, well, that one in red seems more obvious to me. I don't know, they're the same, they'll give you the same answer. So then I have 1/2 r squared d theta, don't forget the r squared part, minus, now we need to do this inside loop. So we're gonna have to kind of play around, we're gonna figure out like when is this inside loop starting and when is this inside loop kind of ending at. And when I'm looking at this one, I'm just gonna do again just half of it. You might have done the whole piece. Let's just think about what would happen, what would be the theta that gives you the bottom part of that inside loop. Well, we already saw that 3 pi over 2 gave me the outside one, so what might be an angle you try for that inside loop? Say again, Ben? Pi over 2. The inside loop's often the negative r, but we can go ahead and try it. If I wanted to try theta is equal to pi over 2 as a starting point, plugging it in, 1 minus 2, the sine of pi over 2, it gives me -1. Is that okay? Yes, as long as you stay negative within the entire interval, that's okay. So let's go ahead and think about using the pi over 2. If pi over 6 is where the positive r ended at, where do you think the negative r is going to end at? Based off of where it crosses the pole. I'm not asking this question clearly enough. Let me try it again. If I think about my r value, we saw that at pi over 6, r was equal to 0. At 5 pi over 6, r was equal to 0. We first started off with a positive r. That was like from the negative pi over 2 to pi over 6. What do we think r is going to be between pi over 6 and 5 pi over 6? Negative. There's your inside loop. And then once you get back to 5 pi over 6, you're back on the outside loop. So if I want to deal with the negative r, this is the interval that I'm looking at. So where's that negative r ending at? It's ending at 5 pi over 6. I'm putting it up top because it's bigger than the pi over 2. And then we have the formula 1/2 r squared d theta. And again, I did have to multiply this by 2 because we just did half of it to kind of find that area. So you can kind of see, like, I'm not going to say that this is easy. Like, it takes a lot of practice, I think, to get kind of used to seeing these values, which is why homework is going to be super important for this last topic. But again, they're also, I can just tell you, like, I'm not going to give you the AP exam. I'm not going to give you one that has, like, crazy start and end values as your angle. Like, it's going to be ones that you can either easily figure out by setting it equal to 0, or by plugging in, like, 0, pi over 2, pi, and things like that. Seth, you have a question.
Where did the pi over 2 come from on the second interval?
The pi over 2, when theta is pi over 2, your r value is -1. So like pi over 2 is up here, but -1 puts you down, so you were here. So basically, if I'm tracing out from pi over 2, you're here, and then 5 pi over 6 comes after that, which is basically happening right here. So it's basically talking about this interval from here.
Mr. Brown, why'd you pick pi over 2? I don't get how you're picking the angles.
You don't get how I do what?
How you're picking the angles. It just seems random.
It's not random. I mean, I guess part of it is maybe we should have spent more time graphing polar functions, so we've forgotten how to do those. But like these graphs, like clearly, I think we should know that like a point down here, this is 3 pi over 2 or pi over 2. Like this point down here can't be pi over 6 because of where it's located. You have to still think about the unit circle working. And again, I'm trying to find a value when I plug it in that it gives me the R value that I need. The short answer and kind of be the longer way, like if we can't figure that out by just guessing, you're going to be solving a bunch of equations. Like you're going to figure out, hey, when is R equal to 3? Set this equal to 3 and solve for sine. When is R equal to 1 or negative 1? Set your equation equal to that and solve. So it's going to be a whole lot easier to just know that when I'm talking about these key values, they're going to be happening at either 0, pi over 2, pi, or 3 pi over 2, or key points are going to happen when it crosses the pole when R is equal to 0. And I feel like I didn't answer your question, but a lot of it does kind of come down to just seeing some more examples and then maybe form your questions that way. Which is kind of a bad answer for me to say.
Mr. Brown,
Yes.
on that graph you drew with the R and the positive sign and that line on the right,
Yeah, so
how did you know it was like negative after like a certain value?
because I mean a lot of it is I'm just thinking about what this graph looks like. So again, if I'm thinking about if I go back and relate it to this graph that I related it to, and this might help some of you see it. This peak right here, where you see my cursor, that's at negative pi over 2. And like I can even like prove that to you, calculate value, negative pi over 2. It's right there, like that's the furthest away in the outer loop. Then we traced in, this first coordinate right here is at pi over 6, that's where we're at the pole. There's your inside loop. Your inside loop is ending at 5 pi over 6. What did we write the inside loop as is we just wanted to write half of it. Half the inside loop is going from pi over 2, that's the peak of it down here, to 5 pi over 6, and then you basically repeat it again. So a lot of it is just me looking at this and kind of thinking about outer loop and then inner loop and kind of making sense of it that way.
Is there a way we do it without having that graph? Like just knowing without that graph?
You can make like a quick t-chart and plug in key values of 0, pi over 2 pi, 3 pi over 2, and 2 pi. And that will give you 4 points to plot, and you kind of want to see how it works from there. So if you were doing it that way, and I'm more than happy to show that to you. Like if you didn't want to look at the graph, I might say, hey, let's just think about what it's doing as we go around like this. Of course, I skip over pi. And then just plug it in. So like the sine of 0 is 0, so we have 1. At pi over 2, that's going to give you negative 1 for your R. At 3 pi over 2, that's going to give you 3. Back at 2 pi is going to give you 1. So if I'm tracing this, at 0, we're at 1. I skipped over pi. At pi over 2, we're at negative 1. Here's pi over 2. We went down, opposite direction. At pi, we're at 1. At 3 pi over 2, we're at 3. So I can kind of figure out how it looks based off of that information. So I knew that it was negative close to pi over 2 and switches whenever it's crossing the pole at pi over 6 and 5 pi over 6. Which is why I'm also going to say like a lot of these problems is going to be best like as you work on the homework, because it sounds like we might, I mean, I know I definitely probably should have spent more time reviewing the polar graphs, but like getting a feel for how these polar graphs work while you're doing the homework. So I'm actually going to go ahead and let y'all start homework. I can tell we're definitely going to have to go over this again tomorrow, but that's fine. I'm not worried about that. But homework-wise, what you're able to do, you're now able to do all of homework's numbers 1 through 5. That homework 5 is going to be the one that has a lot of the polar areas on it. Continue working on the homework. Tomorrow we'll regroup. I'll definitely write some more area problems and share them with you just so we can kind of talk about them. I think that would be beneficial. Then you have the briefcase binder and then testing on Thursday. But you still have plenty of time to practice, so I don't want you to stress about that test. And I'll do my part and come up with a few more area problems to talk about as well. Any questions you want me to answer now before you get started?
Yeah, I have a question, real quick.
Hold on, my sound on my computer is not acting right.
If you right click, go back to the resume.
There you go. This works. I got it. Say it again.
Yeah. So for example 3 that you used,
Uh-huh.
you didn't pick any thetas. Like I got confused because one of them you picked thetas and like we just picked them, and for this
Mhm.
one we just plugged in. And when do you know to like? I just got confused. Does
Like,
that make sense? What I'm
yeah,
asking?
no, I get what you're saying, and like the short answer is like I just kind of look at what I'm trying to find the area of and just go with it. So like for this one, I didn't pick angles because I just wanted to find the area of a full petal. Now what I could have done, I didn't do this, but like if I wanted to be, I guess, even more complicated, I could say like, well, maybe I just want to find the area of half a petal, which I could have done. And I could have found the area of half a petal and just multiplied it by 6. And if I was doing it that way, then yes, I probably would try to pick some values. What values would I want to pick? I would want to find the one that gave me that maximum value of R, which would be 6. That one would be a harder one to do because I have to figure out like 3 times something and kind of go from there. And so a lot of this is just going to come into play, like what you're considering is like, what's going to make this easiest for you to set up the integral. Like, yes, you could set up and just find the area of half a petal, but why would you waste your time and try to find what angle this is when you can just find the entire area and multiply it by 6? Same thing if I kind of go off of, because another one I picked an area for was this one. And like, I know we picked like, I said, hey, let's try 0, let's try pi over 2. Because ultimately I find that's going to be the faster way to do these problems. The longer way to do it would have been like, okay, well this area is starting when I'm at the pole. So let's figure out when this equation is equal to 0 and kind of go from there. So like, I know I asked y'all in general, like which angles you would choose, and that's why I chose 0. But realistically, if I'm doing this problem, I can look at that R theta and know that if theta was 0, the R value is not going to be 0. So I would go ahead and choose a better choice. I'm going to choose the one that's going to give me an R value that makes sense, that's going to put it where I want it to exist at the pole. If that, I don't know if that makes more sense or less sense.
Yeah, because when I looked at it at the beginning, I was like, why don't we just plug in 0 as R?
Yes,
and
so
figure
then
out
you're
what's
probably thinking ahead and being more smart about it and choosing the better option. And that's kind of what it is, like you just want to figure out the angles that work in the best way possible.
Okay. So if we have a graph, we could just plug in the R and just get the theta, right?
Basically, you're looking for the thetas that give you what you want, depending on if you're on the pole or away from the pole.
Gotcha. Okay. Thank you.
And you'll always have the graph. The only examples I've seen where you haven't been given a graph in the AP exam has always been a calculator section. So like you will always have the graph in front of you for these problems. But yeah, I know we're running out of class time, like literally a minute. Work on as much homework as you can. Obviously, I know you're really busy in a lot of your other classes. But do as much of the homework you can. Tomorrow, I will try to pull out a few more area problems, just to make sure we get the hang of it. And then we'll kind of pick up from there tomorrow. But yeah, class is ending, so y'all can go ahead and get ready for your next period. We'll regroup and kind of do some more of these area problems